session 6, I believe. Yeah, I've forgotten. Okay, so all of us are aware of how to find the inverse Laplace transform when we are giving the expression. One side note is when we have an improper, this is very weird. Okay. So one case is where we have an improper fraction, right? So both the numerator and denominator have a degree of 2 over here. Okay, so n and m is 2 over here. They have the same degree. And when they have same degree, then we cannot do partial fraction expansion.
Long division?
Yeah, so first we'll divide this and then get a proper fraction and then go forward. So a shortcut or a technique to do this is the first term that you'll have is the coefficient of the highest term of the numerator, that's 2, plus some constant over the root factorized. Okay? So this is a standard technique. Your constant term will be the coefficient of your highest degree, that is 2 over here, and then you'll have the partial fraction expansion of the factorized denominator. The denominator factorizes to s plus 1 into s plus 2. Okay? And then we can proceed forward. So whenever the numerator and denominator have the same degree, you always have a constant term. Okay? And this constant term always translates to what? What is the inverse Laplace transform of a constant? Anyone remembers?
That direct delta.
Correct. So you'll have 2 delta t. Okay?
What is it? 1 and 2 again?
Sorry?
Is the denominator.
So this denominator, s square plus 3s plus 5, this factorizes to s plus 1 into s plus 2, I believe. Something else. Yeah. Okay, so this is just factorization of the denominator.
Yeah, it's a 5, so I think factorizes it.
Oh, incorrect. Sorry. Let me cross check. Anyways, whatever this factorizes to. Find your answer. Yeah. Okay. So that's the case when you have the same degree. Always you'll have a constant term, and that will always translate to a direct delta in time domain. And this is a small technique of how to do this, get this expansion
you make
without.
5 or 6, it will work.
Okay, so 5
No,
and.
no, keep the 3. But
Okay, keep the 3.
That one becomes a 6, yeah. Yeah, 3 and 2.
And 3 and 2.
Oh, I'm sorry, 2 and 1.
2 and 1.
Yeah. Or no.
No.
No. Make that 3 or 5. Yeah, make that 3 or 5. Yeah, make the 3 or 5 or there. 5 and 6.
5 and 6?
Yeah. Now we go.
5 and 6, and then it'll be 2 and 3.
Yeah.
Okay. So this becomes s square plus 5s plus 6, which translates to s plus 2 and s plus 3. Okay. Great. We just created a problem. Okay, briefly I'll go over some of the properties of Laplace transforms. So in your upcoming homework as well, you will be using these properties. And remember that all of these properties translate to unilateral Laplace transform. Okay? It's not from minus infinity to infinity, 0 to infinity. All right. So first, very straightforward property is scalar multiplication. So if your x of t has a Laplace transform x of s, a Laplace transform pair is always denoted with a double-ended arrow. Okay, so it's like x of t, you take the Laplace transform, you get x of s, and if you take the inverse Laplace of x of s, you get x of t. So this is your common notation of a Laplace transform pair. Okay? So whenever you're writing that x of s is a Laplace transform of x of t, write it in this notation. Okay? Okay, so if x of t has a Laplace transform x of s, what will be the Laplace transform of x, kx of t, where k is a scalar? Correct. So your Laplace transform, that is x of s, just gets multiplied with k, because your k comes out of the integration that you do. Okay? So scalar multiplication is straightforward. Then the standard time shift property that all of you are aware about. So if x of t has a Laplace transform of x of s, then x of t minus t naught, ut minus t naught, has a Laplace transform of x of s e raised to minus s t naught. And t naught here is greater than or equal to 0. Sorry. Okay. So whenever you have a time shift in time domain, you'll get an exponential multiplied in the s domain. All right. Now, time differentiation. And there's a reason why I'm calling it time shift and time differentiation, because you have similar properties for frequency shift and frequency differentiation. Okay, so do not get confused with the terms. Okay, so time differentiation is straightforward again. If x of t again has a Laplace transform x of s, then what is the Laplace transform of the derivative of x of t? So your Laplace transform just gets multiplied with s minus your initial condition. And this will be given to you. Okay? So this is 0 minus. This is your initial condition. Anything before 0. Alright? So this is initial condition. If you're taking the second derivative, your Laplace transform gets multiplied with s square. Your first initial condition gets multiplied with s, and the derivative of your initial condition comes next. Okay, and then this goes on and on and on as your degree increases. All right? Everyone done? Okay. Let's continue with. You're done? You got it? No? Okay. I'll just. It should come in focus. Yeah. Yep. Derivative. Okay. Right. So if you have a differentiation property, the integration property is next. So that was 1, 2, 3, 4. Sorry. So time integration. So x of t has a Laplace transform x of s. Then what is the Laplace transform of integral of your function? It is just x of s over s. Okay, so differentiation you multiply with s, integration you divide by s. You can remember it that way. All right. Now, as we had time shift, time differentiation, time integration, we have frequency shift, frequency differentiation, and frequency integration. By frequency here, I mean the s domain. My e raised to power s omega naught t represents a frequency. Okay, so frequency shift. So xt again has Laplace transform x of s, but now my Laplace transform is x of s minus s naught. I have a shift in s domain, not in the time domain. Now this translates to an exponential multiplied with my function. All right, just be careful with the signs. When there was a time shift in your time domain, you had a negative exponential, whereas over here you have a positive exponential. There's no minus sign in the exponential. Okay, so don't get confused with the signs. All right. Next property is frequency differentiation, wherein xt has Laplace transform x of s, and you take the derivative of x of s with respect to s. Okay, this will have an inverse Laplace transform of minus t xt. Okay. All right. So even in case of time differentiation, my x of s was multiplied with s whenever my x of t was differentiated. Over here, your multiplication with minus t. Okay, and then there's no question of initial conditions. The question of initial condition only comes when you're differentiating x of t or integrating x of t. Okay, next is frequency integration. So again, x of t has Laplace transform x of s. Now if this thing is represented as an integration, this will translate to x of t over t. Okay? Again, similar to time integration, whenever there's integration, you're dividing by the variable that you have. All right. Any questions? Okay. Next is scaling. So if x of t has Laplace transform x of s, x of at, here a is greater than 0, will have a Laplace transform 1 over a, x s over a. Okay. So if my a is an integer value, say 2, 3 or 4, that means I'm compressing over here, then I'll get an expansion in S domain. So compression in time domain will be expansion in S domain, compression in S domain will be expansion. Did I say it right? Yeah, compression in time domain will be expansion in S domain, expansion in time domain will be compression in S domain. Okay? All right. Next property is if you have two functions, let's say x1t and x2t. x1t has a Laplace transform of x1s and x2t has a Laplace transform of x2s. Okay, and I'm convolving x1t with x2t. Okay, so this I can solve as the product of x1s and x2s and then take its inverse to get my answer. Okay, so convolution can be done in time domain or in S domain, the frequency domain. Convolution becomes multiplication in frequency domain. All right, and similarly, multiplication in time domain will become convolution in frequency domain. All right, so this will translate to convolution of x1s and x2s. Okay. All right. Any questions? Okay. Next, one of the things is applying Laplace transform to solving differential equations. So till now we're getting 0 input and 0 state response using characteristic equation. We can get similar solution using Laplace transforms. Okay, so what have we been doing till now is we have a differential equation, and using this we get 0 input and 0 state. So 0 input we got with characteristic equation.
Can we get a 0 state with Laplace?
Yes, you can get 0 state with Laplace.
Without needing to convolution?
Yes. So 0 input we are getting with characteristic equation, and 0 state we were getting with convolution, right? Now we will get this whole thing with Laplace transform. All right? Okay, so I'm going to do an example that's 4.3.1a. So what is given to us is d square plus 3d plus 2 y of t is equals to dx of t. As in exams, some of the students have taken d as a variable and treated as a polynomial. D over here is a differential operator. It's not a variable. Oh, sorry. Okay, so remember that always, never treat your capital D as a variable. Okay, it's a differential operator. So your capital D is equivalent to d by dt. And your function, you take the derivative of your function with respect to t. All right, it's an operator, it's not a variable. Okay, now other thing given to us is that xt is a unit step function, and we have initial conditions being y0 minus is equals to y dash 0 minus is equals to 0. So our initial conditions are 0, all 0. Okay, so we have s square. Yeah, these are given in the question. These three things are given in the question. Okay, so we write this equation in terms of s. We do not treat our capital D as a variable. So s square plus 3s plus 2 ys is equals to s x of s. How do we get this? We are taking the Laplace transform of this equation. So let me explain that to you. The equation that we have is d square yt plus 3d yt plus 2yt is equals to dxt. I'm taking the Laplace of this equation. Okay, Laplace of both sides. Now, whenever I have a double derivative, right, so this is a double derivative, this is equivalent to d square yt over dt square. Correct? Oops, sorry. Right? And when I take the Laplace of this, what will I get? Yt. Correct. I'll get a s square y of s minus s y0 minus y dash 0. And from the question we're given that this is 0. Okay, so what we get is s square ys. Similarly, 3d yt. So 3d yt is equivalent to 3 dy t by dt. Right? Now I take the Laplace of this. My 3 remains the same because it's a scalar. Because of the differentiation I get an s factor, and yt has a Laplace transform of ys. Okay, and then again I have a factor of y0 minus, but this is 0. All right, then 2yt will have a Laplace of 2ys.
So you transform each one by one?
Yes.
But why is 2yt not 2? Why isn't like isn't that like a direct? Okay, you're doing. I don't know
what
y of t has the y of s, but we still don't know what y of t, so we don't know exactly what y of s is gonna be, right?
Yeah.
Okay.
You're just assuming that y of t has a Laplace transform of y of s.
Okay.
Okay, and x of t has a Laplace transform x of s. Okay. Then my dxt is equivalent to derivative of xt with respect to t which will give me a Laplace transform of Sx of s. Correct? Any questions?
Shouldn't it be minus? Oh, because it's zero input, right?
Yes. So,
Shouldn't it be like minus x? Yes.
but my x of t is ut.
Oh, okay, okay.
And u0 minus is 0.
Oh, okay. But 0 plus is 1, right?
We don't care about 0 plus.
Okay, oh, we don't care.
0 plus comes into our signal, right? Our signal starts as 0. Anything before 0 is an initial condition. Anything after 0 is our signal that we want.
And in this case, you can do that because they told you was u of t. I mean, it's not
Yes,
okay.
yes,
Okay.
yes. Okay. Where? Here? Yeah, so whenever you take the Laplace of a derivative, you get S multiplication. Yeah. Similarly, how we got over here. It's the Laplace property, the time differentiation property that we have. All right? Makes sense? Okay. So, we are given that x of t is ut. What is the Laplace transform of ut? Okay, forget it. 1 over s. Okay? So, our final equation now looks like s square plus 3s plus 2 ys is equals to sx of s. S into 1 over s will be 1. Okay? So, my ys is equals to 1 over s square plus 3s plus 2 is equals to 1 over s plus 1 minus 1 over s plus 2. This again you solve with your partial fraction expansion. Okay?
Then you solve everything and you go back to time domain again.
Yes, and now you just use your standard Laplace table, the transform pairs table that you have, and take it back. So what is the inverse Laplace transform of 1 over s plus 1?
Yeah,
Correct. Minus is minus 2t, and u of t will be there. All right? Okay. So 4.3.1 just asked us to solve this equation. Okay? And this is a solution. So whenever you are asked to solve a differential equation using Laplace transform, it's asking for y of t. So, yeah. Okay. Next, we are going to do another example with sort of which has initial conditions. Okay. The initial conditions have some value; they're not 0. All right. So, example 2. We have d square plus 5t plus 6 y of t, d plus 1 x of t. My y0 minus is 2 and y dash 0 minus is 1. So my initial conditions are present. Okay, they're not 0. Right? Now, this equation.
It is not from the book?
Yes, it is from the book. It's an example in the text. Let me get you an example number.
We don't get what x is.
We know. I'm just writing that down. So x of t is e raised to minus 4t u of t. Okay, this is example 4.10. Okay, in your textbook. All right, so this equation is equivalent to my second derivative with respect to t of by t plus 5 into derivative of yt with respect to t plus 6yt derivative of xt with respect to t plus xt, right? Okay, now I'm taking the Laplace of this, both sides, okay, and then again using my properties. So Laplace of my first term will be s square ys minus s y0 minus y dash 0 minus, correct? This will be s square ys minus 2s minus 1, okay? So do not forget about this factor, your initial conditions, okay? Similarly, this term will be 5 into s ys minus 2. This term will be 6ys and so on, and I'll just write it down for you. So my final equation will be s square plus 5s plus 6ys minus 2s plus 11 is equals to s plus 1 over s plus 4. Okay. Everyone knows how we got s plus 1? Okay. Taking the Laplace of this side, my right hand side, I have Laplace, first I'll get x, s into x of s, right, plus x of s, that is s plus 1 into x of s. My x of s is 1 over s plus 4, right? X of s is 1 over s plus 4 because my x of t is e raised to minus 4t ut. Alright, so I get s plus 1 over s plus 4. Okay? Okay. And then you go in the standard form. Sorry? Yeah. My x of t is e raised to minus 4t ut. So I take the Laplace of this, and that's how I get 1 over s plus 4. Okay? Yeah. Now, moving on, my final equation looks like y of s is equals to 2s square plus 20s plus 45 and so on. Okay? And then I do my partial fraction expansion. Okay? This will give me a result of 13 over 2 over s plus 2 minus 3 over s plus 3 minus 3 over 2 over s plus 4. Alright? Now, in this equation, okay, let me recap a bit. I had got this to be my answer after taking the Laplace transform. Okay? Taking this term on the right hand side will give me 2s plus 11 over s square plus 5s plus 6 plus s plus 1 over s plus 4 s square plus 5s plus 6. Okay? This is my 0 input, and the second term is my 0 state. Everyone understands how we got it? Because this first term is only because of our initial conditions. It's not because of our input. That's why it's the 0 input response. Okay? And the second one is only because of the xt that I'm applying. There's no component of initial conditions in this part of the response. So here we have a 0 state response. Okay? Make sense? Alright. and then you take the Laplace inverse transform of both of these separately, so you will get your yt, which will be your zero input response and zero state response. Okay, and then over here, this is your combined response. This is zero input plus zero state. Okay, all right, any questions? Okay, next we'll go on to I'll just finish up writing this thing. So it's 7 s plus 2 minus 5 s plus 3 plus minus 1 over 2 s plus 2 plus 2 over s plus 3 minus 3 over 2 s plus 4. Okay, so 0 input, 0 state, and then take inverse Laplace of all of these terms separately.
We do it separately, we don't do it combined.
Yeah, so if the question asks you to find the zero input and zero state response, then you do it separately. If just it just asks you to find y of t and it does not tell you to find zero input and zero state separately, then you do a combined version of it. Okay. Now, next thing to cover is transfer function. Okay. Now, when we have zero initial conditions, my polynomial with ys is some power of s, so sr plus 1, sr minus 1, and so on. My polynomial with x of s is again some power of s, let's say m, and so on. So let me just call this q of s and this part p of s. Okay, these are polynomials in s whenever I have a zero initial condition. Okay.
Because just in general, what is a transfer function? I mean, what does it tell you?
Transfer function is the Laplace transform of your impulse response. Okay,
It's like the
so your
response in the frequency domain.
yes, so your impulse response is h of t, right? You take its Laplace, you'll get h of s. Okay, this you can find without finding h of t. So if you have y of s and x of s given, then you find h of s, take its inverse, and find h of t.
Also, that's an easier way to find h of t.
Yeah. Okay. The whole point of Laplace is taking your computations in another domain and doing it over there. So you don't have to do anything in the time domain. Okay. All right. Because in time domain, your h of t will be convolution of
You should, isn't it?
no, your y of t will be convolution of h of t and x of t. But in S domain, your y of s will be just a product of h of s and x of s. Taking a product is always easier than a convolution.
Oh, okay, so did you
That's the whole point of Laplace and the S domain. All right, just to simplify things. Okay, so h of s will be p of s over q of s, right? Oops, sorry. Because from this equation, from here, my y of s over x of s is p of s over q of s, and this becomes h of s. All right. Now, what this means in systems point of view is just a small thing. You have an input x of s, you have a system h of s, and your output is y of s. So your y of s is product of x of s and h of s. Or in time domain, it's y of t, which is the convolution of x of t and h of t. Okay, these two terms mean the same thing. All right. Now, let's just do a quick example. So we are given the following equation, which is similar to the last one. Okay. Now, this equation in terms of s is s square plus 5s plus 6 y of s is equals to s plus 1 x of s. This is the case when my initial conditions are 0. Okay? So do not forget about this factor that my initial condition is 0. Alright? So my h of s is nothing but y of s over x of s. So we get s plus 1 over s square plus 5s plus 6. Do a partial fraction expansion. Okay? And then find h of t. Okay? If the question asks you to find h of t, don't find h of t just for the sake of finding it. Okay? If the question asks you to find h of t, that is the impulse response, then find h of t. So h of t, just to be clear with terms, is my impulse response. H of s is my transfer function. Okay? And h of s is just the Laplace of h of t. Alright? Just be clear with the terms that we're using. Okay? Now, if this differential equation is given to me and I have x of s and I know that the initial conditions are 0, I can find what y of s is, right? Y of s will just be h of s into x of s, right? H of s we just found to be s plus 1 into over s square plus 5s plus 6 into x of s. If x of t is given to be, let's say, 3 e raised to minus 5t u of t, okay, then my y of t becomes 3s plus 1 over s plus 5 s square plus 5s plus 6. Do a partial fraction expansion and then you'll have your y of t. Right? Okay? Sorry? Yeah, y of t. After partial fraction expansion, you take your inverse Laplace transform. All right? Okay, so another example is if we have a system called an ideal delay. So what an ideal delay does, it has an input of x of t, and this is my delay system. So delay is a time domain delay, so it's time shift. Okay? And my output is y of t. And this applies a delay of t. Okay? So what will be y of t in terms of x of t? I'm delaying it. Yeah. So x of t minus capital T. Okay? So this is my ideal delay. Nothing else is happening, there's just a delay. Okay? So what is h of s in this case? You can find it from the information that I have given you.
Yeah, I mean,
S over x of s and then e to the negative s t.
H of s, correct, y of s over x of s. Y of s is nothing but e raised to minus st x of s over x of s. So your h of s is e raised to minus st. Okay? All right. So that's with the transfer function. Next thing to do is stability. Okay? Now, In continuous time, when we had a characteristic equation, just to recap, continuous time and characteristic equation, we saw if the roots were in left-hand plane or not, right? That was our condition, that it was stable when all the roots were in LHP, right? Unstable when even a single root was in RHP, the right hand plane, okay? And marginally stable when we had repeated roots on the imaginary axis, right?
Do they have to be repeated, I think, or only one? Is one alone?
No, repeated, because a single root will have the complex conjugates on the imaginary axis, but that does not become repeated. Repeated is when it's at the same position twice. Okay, so that's a thing that you need to be careful about. All right, this was with continuous time and characteristic equation, right? For discrete time, or when we had difference equations, we again found a characteristic equation, and this was in terms of gamma, right? And we said it was stable whenever the absolute value of gamma was less than 1. So we were stable whenever we were inside the unit circle. Right? So these were the terms, stability conditions that we had. And this is for asymptotic stability. That is internal stability. Okay. Bibo stability, on the other hand, is external stability. Okay. So our system is like a black box. We might think that it's stable externally whenever we apply an input and we get a bounded output, but internally it might not be stable. Okay. But whenever it is internally stable, it has to be externally stable. Okay. So Bibo stability cannot say everything about asymptotic stability, but if your system is asymptotically stable, your Bibo stability is guaranteed. All right. Now, stability in case of Laplace transforms that we have. Okay. So, and whenever we talk about stability in this case, we look at the transfer function. That is h of s. Okay. So my h of s is a fraction in terms of, it is a polynomial in s as a numerator, and again a polynomial in s as denominator, right? For stability, we are only concerned with the denominator term. Okay. So for stability, only look at denominator. Okay. Another term that you need to be clear with are zeros and poles. Okay. So zeros are the roots of my numerator. And poles are the roots of denominator. So for stability, we are only concerned with poles and not with zeros. Okay. All right. So what is the condition for stability? Now,
do we do both plots in this class?
sorry?
Do we not do both plots?
I don't think so. We eventually might, but right now I don't think so we'll be doing that. Okay, so the conditions over here are also similar. If all my poles are in LHP, so my system is stable. Okay. If I have a pole in RHP or repeated poles on imaginary axis, my system is unstable. And if I have unrepeated poles on imaginary axis, then it's marginally stable. Okay, all poles in left hand plane, my system is stable. It's unstable whenever there's pole in right hand plane or repeated poles on imaginary axis, and marginally stable when I have unrepeated poles on imaginary axis. Okay, all clear? Any questions? Okay, again we can have a case of bibostability but asymptotic instability. So let me just do an example. Yeah, oh sorry. All good? Should I turn the page? Okay.
Do you upload this one?
Sorry?
Do you upload this one? This goes in the video, right?
This goes in the video,
Okay.
yeah. So the videos are available.
Okay.
Okay, so let's do an example. I have two systems, okay? So my first system has a transfer function of 1 over s minus 1. And this I'm denoting as h1s, okay? And I have a second system which has a transfer function of s minus 1 over s plus 1. Okay? Now, where is the pole for this first system, h1s? Right. So pole is at s is equals to 1. That means it is in right hand plane. That means it is asymptotically unstable. Correct? Alright. For my second system, where is my pole? Correct. And I have a 0 also. Where is my 0? Correct. But I don't care about the 0 for stability. Okay? Now, here my system is asymptotically stable. Right? But when I have this system in cascade, so let's say I have a third system now, which is my h1s followed by h2s. Okay, so this is what I mean by cascade. They're in serial connection. That's it. So this combined has a transfer function h of s, which is h1s into h2s multiplication. So I'll get a transfer function of 1 over s plus 1, right? And now my pole is at negative 1, right? So this system is stable now. Right? So I can combine an unstable system with a stable system. So what is happening here? The 0 of my second system is cancelling the effect of the pole of the first system. Okay. Any questions on this? Right. And this is bibostable. Okay. Right. So this is bibostable. Which one? H2S? No, so 0, we don't care about the 0. All we care about is the poles for stability. Okay? Now, if you look at this composite system, my h of t is now e raised to the power minus tut, and it's decaying with time. So I have bibostability, right? But for asymptotic stability, both of these systems are independent of each other. Okay? So although this system is stable, this system can still internally go unstable. Right? Because this has a pole at 1 and this has a pole at -1. Okay? So asymptotic stability is not there. Okay? I have bibostability, but I don't have asymptotic stability. Make sense? Because the poles are there, they've not vanished. Okay? Combined effect, I get a stable system, which is bibostable, but individually these systems are different, they're independent of each other. Okay? So this system can still go unstable internally. Alright? Any questions till now? I think that's it for today. Okay? And I'll be here for my office hours. Thanks, Andrew.
Can you show us again the notes where you have like the criteria for stability, like the poles?
Sure. This one, right?